In 10.2, we're learning something very similar to what we did in 10.1 with proportions. Now we're just using the same thing, but with means. So we're combining two samples and we're talking about the means of them and comparing them. So for the first one, it says in a study of heart surgery, one issue was the effect of drugs called beta blockers on the pulse rate of patients during surgery. The available subjects were divided at random into two groups of 30 patients each. One group received a beta blocker, the other group received a placebo. The pulse rate of each patient at a critical point during the operation was recorded. The treatment group had a mean pulse rate of 65.2 and standard deviation of 7.8. For the control group, the mean pulse rate was 70.3 and the standard deviation was 8.3. Find the standard error for the difference in mean pulse rate between the two groups. First, define the two parameters. So the mean pulse rate for group 1, I said, is the true mean pulse rate of patients that took the beta blocker. And for the mean of group 2, it's the true mean pulse rate of patients not taking a beta blocker. For the standard error, we do the sample means for each of them. So 7.8 squared over the sample size for the first one, which is 30, plus 8.3 squared over 30, and you take the square root of that, and you get 2.08. So then part B says to construct and interpret a 99% confidence interval for the difference in mean pulse rates. So that is a state plan do conclude. So for the state, I say for the mean of group 1 and the mean of group 2 defined above, we wish to construct a 99% confidence interval for the true mean difference in pulse rates, mean 1 minus mean 2. You have to say how you're subtracting them, and you also should define them, but because we did it above, I just said this right here. For the plan step, I said it's a 2-sample T interval because we're using means for mean 1 minus mean 2. Random, they're divided at random into two groups, and so we're told that it's random. For the 10% condition, we actually don't have to check that because this isn't a situation where we are like having a big group of people and we're pulling out 30 random people. We have 60 people and we're splitting them into half. So it's not a sampling without replacement situation, and the patient's responses should be independent from each other. What's happening with one patient shouldn't have anything to do with what happens with another patient. So even though the 10% condition doesn't apply, this is an independent situation, so we can keep going using those formulas. And then for normal, because each sample individually is greater than or equal to 30, it actually is 30, then it meets the condition for the central limit theorem, which says that the sampling distribution of x bar 1 minus x bar 2 is approximately normal, which is good. For the do, I say the formula first in words, so point estimate plus or minus margin of error. Then I say it with the value, like in numbers, or I guess in letters, like the actual formula. So the point estimate is x bar 1 minus x bar 2. That's the observed difference, plus or minus t star, and then the standard error. So the observed difference is 65.2 minus 70.3. Plus or minus t star, and because we're looking at a 99% confidence interval, that means there's going to be, if we want the middle 99%, we have 1% on either side, or we have 1% total on either side, which means a 0.5% here and a 0.5% here. So that's why you use 0.005, and then you use n minus 1 here to get the degrees of freedom. And then the square root of 7.8 squared over 30 plus 8.3 squared over 30, which we already did that to get 2.07 here. I must have rounded differently. So in actual, like what it actually equals, you get your point estimate plus or minus this times this gives you this for a margin of error. So when you subtract that and then you add that, you get these two values here. So that is your margin of error, which means we are 99% confident that the interval from negative 10.83 to 0.63 captures the true difference in mean pulse rates of patients who took beta blockers before surgery and those that took a placebo, which on a side note means that we do not have convincing evidence that there's a difference, because no difference would mean that when you subtract and you get 0, and 0 is within our confidence interval. So we do not actually have convincing evidence here that there is a difference. Then part C says, suppose we want to test the hypothesis that beta blockers reduce the mean pulse rate. State the null and alternative hypotheses for this test. Well, the null is that there is no difference. That means when you subtract them, it equals 0. And the alternative is we're wondering if beta blockers reduce the mean pulse rate. So that means that the mu sub 1 here, because that is the, we defined it up here, is the beta blocker group, is the 1. If theirs is smaller than the people that took the placebo, that means when you subtract the bigger number from the smaller number, you would get a negative number less than 0. So that's the alternative hypothesis, that group 1 minus group 2's mean is less than 0. And then on the last part, part D, says the test statistic is negative 2.453. Determine the p-value and draw an appropriate conclusion using alpha equals 0.05. So if that is the test statistic that we got, that's like the z-score essentially, but it's like a t-score. You can plug that in here. So I did t-CDF, and I got from negative infinity to negative 2.453, and 29 is our degrees of freedom. And we get this value right here, 0.0102. That means that this probability out here is 0.0102, or about 1%. So I said, assuming that the null is true, there is a 0.0102 probability of getting the observed difference or more extreme purely by chance. Since 0.0102 is less than 0.05, that's the alpha that we're comparing it to here. That's a significance level. That means that we have convincing evidence that there is a difference in pulse rates between patients who received a beta blocker and patients who did not, so we reject the null. This is interesting because we actually got a different result doing a significance test than we did doing the confidence interval. But you can tell that it's actually pretty close. Like 0 is not right in the middle of this confidence interval. It's right on the edge of the confidence interval. So it makes sense that it would be, kind of doubtful. So that's all.